So, yeah, okay, great.
Okay.
We're there. Okay.
Now, can I still get my slides moving? Yes. Okay. So where were we? So they're eroding basalt. That's the key thing. And they breach these divides. And that's a very diagnostic feature of subglacial channels. And in the glacial world, when we have these types of channels that have all these characteristics and the association between uphill crossing or divide crossing channels overlain by moraines and often also hosting eskers within those channels, these are all the hallmarks of what we call tunnel channels or tunnel valleys. You may have heard these different terms. So that's what we interpret these channels to be. This is a scabland landscape, but it's a scabland landscape formed under ice. It's made by water, just like any other scabland, but it's made by water flowing under ice, under pressure.
Okay.
This is not a the concept of tunnel channel and tunnel valleys and glaciated landscape is not something new. People have described these types of landforms and these landform associations with eskers and so on for decades and decades, if not centuries. But this is just a recent example from an article from the Scandinavian ice sheet, but I could also pluck examples from the Laurentide ice sheet. And the key things to realize here is, first of all, the orange areas are the main channelized areas. They're called meltwater corridors in some parts of the world, but they're really synonymous with tunnel channels. So orange areas are these channels. You'll notice the similarity in the anabranching, the splitting and rejoining, and there's widenings and over deepenings and sometimes narrowings. There are eskers that occur on the or within these channels, just like we see on Waterville and Omak plateaus. And so for us, that's a completely analogous landscape to what we have in central Washington. So let's just make an early statement, I guess, at this point. This enigma of water supply to Moses Coulee, we feel, is not really an enigma. There's not much of an enigma. There's a very clear water supply to Moses Coulee, and that water supply is this subglacial channel network. The fact that we can see convergence of this network into the head of Moses Coulee is, for us, suggesting very clearly that it's one of the main supplies of water to that coulee. The enigma really only exists if we expect Moses Coulee to have exactly the same type of subaerial connection as we have with, say, the Grand Coulee or the Telford Crab Creek or the Cheney-Palouse tract. But if we sort of reconceive a bit of the configuration of the drainage network and the water supply that goes into Moses Coulee, there is a perfectly clear channel network that leads into that coulee and that can supply it with water. And for us, that's that subglacial network. So if we're talking about subglacial water flow, what does that actually look like? And there's a number of different configurations. So I'm going to just sort of touch on some of these and give you some examples of how this might operate to really try to drive home the point that this is I think, a reasonable interpretation of the process and the network. So lots of different configurations. I want to make it clear right off the start that these are not just sort of fanciful notions. There's a some very good and a pretty robust set of publications on water flow through glaciers. In Iceland, they've been studying these events for decades and decades, Jökulhlaups as they're known. And there's even an article from a few years ago that tries to kind of typify or offers a typology of the types of Jökulhlaups that can happen, the different ways in which we can store and release water subglacially. So I'll refer to that article from Matthew Roberts. In this case, he's got these different types of Jökulhlaups that operate under different conditions. But the point is that all of these types of Jökulhlaups, all these configurations of drainage have really sound observational and physical basis. So one of the more obvious examples of water supply through glaciers is what we observe in Greenland, almost on a seasonal basis and increasingly so every year. This is surface melting and pooling or ponding of water on the surface of the glacier or the ice sheet. Think of the Greenland ice sheet or the margin of the Greenland ice sheet, but transfer that to the Okanagan lobe surface, seasonal melting and pooling of water on the surface of the Okanagan lobe, and then penetration of that surface water through fractures and crevasses to the bed, and then flowing at the ice bed interface, either in this distributed anabranch network system to produce the channel. There's a simple animation to represent what's happening in Greenland. You can see that on a seasonal basis, the zone of melting where we create these lakes is increasing. You can picture exactly the same scenario at the tail end of the last glacial cycle, as Okanagan lobe and the southern fringe of the Cordilleran ice sheet is deglaciating and melting rapidly, we'd be producing enormous amounts of surface water pooling into lakes and potentially connecting. You can see the connections on the diagram as the surface lakes connect through fractures to the bed and then ultimately drain after having been routed subglacially. So it's in this subglacial routing that we're creating the channels that overcome some of the topographic highs. One of the interesting questions for us is, can we generate enough water to create this whole network by this mechanism of surface melt and connection to the bed? And I'll show you how we're approaching this problem and where it's pushing us or where it's leading us in terms of an answer. To be able to answer this properly, we really have to think about the time frame that we have for channel development. So we need some time constraints in terms of how long does the Okanagan lobe spend on Waterville Plateau and on Omak Plateau to create these channels. We know from existing work, mostly that of Richard Waite, that there's a minimum of 4 floods. Richard Waite has proposed at least 4 floods down Moses Coulee. There are some new age constraints from surface exposure dates. This is some of Joel Gombiner's work from his thesis that brackets these dates or the time period for these 4 floods somewhere between 17.4 to 15.5 thousand years ago. So we got about a 2,000 year window. We also know from the work of Atwater in the mid to late 80s in the Sandpool alarm that Lake Columbia, this is the varv count of Atwater, gives us potentially 1,500 to 3,000 years, depending on how stingy, as he called it, or generous we want to be on the counting of varves, so annual layers of sedimentation in Lake Columbia. The count leads us to a duration of the lake for about 1,500 to 3,000 years. And that's important for us because Lake Columbia exists due to blockage by Okanagan lobe. So that count is important because it tells us when Okanagan lobe has crossed the Columbia River to block Glacial Lake Columbia, and also tells us when Glacial Lake Columbia is gone. In other words, Okanagan lobe has retreated enough to allow for the drainage of Lake Columbia. That's a 1,500 to 3,000 year window, depending on the varv count. And again, some dates in terms of the encroachment and retreat of Okanagan lobe. So the timing of approach, crossing the Columbia to the Withrow Moraine and retreating from the Withrow Moraine. The age there, 15.9, almost 16,000 to about 14,000. So the window, really, where we can form these channels is somewhere in the order of 1,500 to 2,500 years. That's the time span we have where we have ice coverage over Waterville Plateau. Now, if we look at some modeling on erosion of bedrock channels subglacially, there's an interesting study that leads us or gives us some answers, but it's not perfect, and you'll see why in a second. That modeling study proposes that seasonal flows, so just regular seasonal melting, which could involve pooling of water on the surface, as I was showing you in the animation, and movement of that water to the bed and then draining subglacially. This seasonal cycle of water production and reoccupation of channels through a glacial cycle can create channels on a timescale of about 4,000 to 7,500 years. So that's actually much longer, requires much more time than we have for 2,000 years of occupation over Waterville Plateau by the Okanagan lobe. So there's a bit of a discrepancy there. The other thing to note here is that the discharges that are modeled are somewhere on the order of 10 to 10 to the 3, so 10 to 1,000 meters cubed per second in terms of discharge. So with those discharges, over that time duration, we can create some bedrock channels, but we're dealing with a much shorter time period. Now, there are some caveats here that we need to think about. Firstly, Moses Coulee and all the other channels are eroded in very jointed columnar basalt. This is recognized to be something that would probably lead to faster erosion. It's that much easier to erode, especially by a mechanism of hydraulic plucking, to erode these columns of basalt. The modeling of erosion of channels that I'm referring to only deals with erosion from the standpoint of abrasion. So there's a bit of a disconnect there, and it's unclear whether or not on the efficiency. On the other hand, the channels that we've mapped are much wider, much deeper, and than those that are modeled. So they should require more time and potentially higher discharges. So we've got an idea of the time that might take. We might be short in terms of our ability to produce this with a seasonal supply of water. And we're dealing with much larger channels, but those channels might form more efficiently because of the plucking. So this is a tricky angle, a tricky argument, simply because of some of the unknowns and the difficulties in comparing. But to our mind, even specifically because of the discharges involved in the modeling, we think that there's a good case to be made for the fact that these channels just require more than simply seasonal water production and drainage. To produce this channel, we need to deliver far more water and over a much shorter period to be able to create this network. So we can look at other configurations, other ways by which we store and release water. And so this prior example of surface drainage to the bed, this was a type 2 yokel in that nomenclature from the article. This is what's called a type 4 yokel, but a type 4 yokel is one where there is a subglacial reservoir of water. Think of it as a pool of water under the ice that builds and builds and builds to a point where it exceeds a threshold and then drains very suddenly and delivers a far greater volume of water than the surface melt that is produced seasonally. So we're invoking a combination of factors, probably some contributions from surface melt, but also a longer term storage of water under the ice and release of that water. We might ask ourselves, so is that a reasonable proposition? Is there evidence we can use to infer the presence of one of these types of subglacial reservoirs leading into this network of channels? And the answer is yes, and I'll just walk you through some of that evidence. We'll focus on Okanagan Valley, but because we're invoking larger quantities of water, we also have to expand our view and our zone of interest beyond the immediate areas of Waterville and Omak Plateau. We're going to have to cross the Canadian border and move into Okanagan Valley north of the Canada-US border. If we go there, what we realize is, first of all, Okanagan Valley is a very deep valley. It's scoured below sea level. It's got a sediment fill that's relatively young. I'll show you some cross sections in a second. But hydraulic modeling of the Cordilleran ice sheet pinpoints Okanagan Valley and other major valleys in southern British Columbia as likely places to pool subglacial water. There's a natural tendency to store water in these deep valleys. That storage and that production of water is likely enhanced in southern British Columbia and in the Okanagan by the fact that there's a number of Eocene volcanic areas and centers that have very high geothermal heat fluxes. So you can see here, for example, the numbers that you see on these diamonds and these points. These are all areas where we've got either hot springs, and that's the temperature of the water, or an anomalously high, geothermal heat flux. And this has been operating since the Eocene. And so it's reasonable to think that during glaciation, this high heat flux contributes strongly to melting and producing water at the base of the Cordilleran ice sheet and storing it in this naturally deep trough that is Okanagan Valley. We can even examine further north, and this is actually harkening back to Brett's and his early forays into British Columbia, looking for evidence of subglacial volcanism. But there is evidence of subglacial volcanism in southern British Columbia. There's the Wells Gray volcanic field that has diagnostic volcanoes called tuyas that are clearly erupted under the ice. So we've got multiple lines of evidence that support this notion of production of water under the ice and storage in the valley. The valley itself is intriguing. It's intriguing because of its depth. It's extremely long. You can see it on the maps. It's hundreds of kilometers long, but it's also hundreds of meters deep, scoured below sea level, and filled with a relatively simple and young valley fill consisting of gravel, sand, and some lacustrine sediments. It's actually remarkably similar to the valley fill and the valley structure of Lake Pend Oreille, which is right in the floodway of water draining and transiting from Lake Missoula into Lake Columbia. Very, very similar architecture of the deposits. And this has been interpreted as a young, and by that, late Wisconsin is what I mean by when I say young, late Wisconsin fill of sand and gravel, mostly reworked sediments by meltwater. And the same argument that we used in terms of identifying diagnostic features of channels, the tunnel channels that we invoked earlier, we see them in southern British Columbia along the flood path and along the proposed route of water in Okanagan Valley. There's bedrock canyons where if we plot the long profiles, you can see on the right-hand side, the change in elevation. There's a clear escalation of the flows or the floor of the channel, gaining in some cases hundreds of meters in elevation. And that's something that we can only do under pressurized water conditions. Rivers will not erode these types of channel profiles. And the tunnel valleys continue, the tunnel channels. I'm using the terms interchangeably. We're right back to Omak Plateau now. If you see my cursor, there's Omak Plateau. It's showing you the channels on that surface, but flanking that, Omak Lake, another area called Soap Lake Valley here. These are bedrock carved channels. These are the long profiles. You see they're irregular. They've got that diagnostic up and down topography that is a telltale for pressurized subglacial water flow. So if we expand, we go back to this map, but we add these components, we realize that there's actually a far greater and more integrated subglacial drainage system. There's absolutely what we see on Waterville and Omak plateaus, but it is congruent, or it is regionally consistent with water flow along Okanagan Valley, likely originating further north on the Canadian side of the border, but flowing in the confines of these big bedrock channels that include the Soap Lake Tunnel Valley and the Omak Lake Tunnel System. This is an integrated channel system operating at different scales. So one interesting question is, how much water can this subglacial channel system convey? And it's an interesting question because modeling, ongoing modeling, this is hydraulic modeling of some of the floods from Glacial Lake Missoula and Glacial Lake Columbia, suggests that Moses Coulee, the dimensions of Moses Coulee are such that we can convey mega flood scale discharges through the coulee. In other words, discharge can reach 10 to the 6 meters cubed per second. So at least 1 million cubic meters cubed per second in terms of discharge. So we're using that as a constraint, and we're going to make some estimates. And I'll emphasize that they're just that. They're estimates because it's difficult to constrain, but it gives us some boundaries in terms of what we can envisage for flow magnitudes through the subglacial channel network. So what we've done is take the cumulative cross-section of all these channels in the subglacial network that we've mapped, and we've taken that at the divide crossings. We've taken that as a common reference point, is where they cross the divides. We add up the total cross-sectional area, and we come out with a number around 104,000 square meters of cross-sectional area. For comparison, portions of Upper Moses Coulee, depending where we establish the depth of flow, the cross-sectional area, or the wetted perimeter, is about 137,000 square meters. So we're a little shy of the cross-sectional area of Moses Coulee, but we're still, into a very large cross-sectional area. We need, if we have a cross-sectional area to get a discharge, or volume of water, we need a velocity of flow. And to do that, we're making estimates based on the diameter of rocks or clasts that we find either in the subglacial channels or in bars within Moses Coulee. So we've got in the subglacial channels a mean diameter of about 60 centimeters. That's the size of the boulders that are in the channels themselves. And the inference here is that any material smaller has been washed away, and therefore the diameter of these boulders fixes or tells us a limit to the energy of the flow, because these boulders are preserved. In other words, everything smaller is moved, anything bigger than about 0.6 stays in place. On the channel bars, the diameter of the boulder is even bigger. It's over a meter, 1.14 meters on some of those channel bars. So the velocities we can infer from this, and there's some relationships that have been established long ago, is somewhere on the order of 6.5 to 8.5 meters per second. At that velocity, we preserve boulders of that size, and we wash away everything else. So if we combine the cross-sectional areas and the velocity estimates, we end up with a discharge through the subglacial network that's on the order of 6.8 to 8.8 times 10 to the 5 cubic meters per second. So we're not quite reaching the sort of threshold for calling something a mega flood at 10.6 cubic meters, 10 to the 6 meters cubed per second, but we're awfully close, especially on the high end at 8.8, we're awfully close. And there's some caveats here, of course. Like any of these modelings, we make some assumptions. But for us, the velocity we infer from the boulders is probably an underestimate, because the rocks, the boulders are preserved, and especially on bars, this is a depositional phase of the flow. It is not peak discharge moments. At peak discharge, we may not be doing any major deposition. So there's a good chance that we're underestimating the velocity we infer from the boulders, because those boulders are deposited late, or if you want to think of it this way, during the falling stage and the falling limb of the hydrograph. It doesn't represent the peak in discharge and velocity. And in other glacial systems, the velocities are frequently above 10 to 15 meters per second. So if we add a bit of, or if we make a few allocations for some of that variability, we're getting awfully close to the mega flood scale discharges. There's also some uncertainty about the cross sections of Moses Coulee. If we take today's cross section of the Moses Coulee and the elevation of the valley floor, or the Coulee floor, and we say, okay, it has to be full of water right to the brim or right to the high water marks, then we end up with a certain number in a cross-sectional area. But the reality is that in many of these bedrock types of canyons or these channels, there's a coevolution of erosion of the channel during the peak and discharge. In other words, the floor of the channel deepens as it erodes during the event where the erosion takes place. And we don't know where the floor of Moses Coulee started. And so there's some uncertainty in terms of what we assume to be the proper cross-sectional area of Moses Coulee. I hope these caveats come through clearly, because they really affect the calculations, and it's difficult to constrain these. So we really have to just accept the fact that they're kind of first order estimates, but importantly, they put us in the right ballpark. That's a really critical part of this, is that we're not that far off from the proposed mega flood scale discharges through Moses Coulee, and that channel network can accommodate that. Before I wrap up, we need to go back to the existing ideas of how Moses Coulee forms and the ones that are currently accepted. So we're going to look at two scenarios that invoke, instead of thinking about a subglacial network of channels, invoke overspill or diversion. And these are two different models that I'll sort of walk you through and explain some of the key ideas and maybe some of the limitations. The first one is this idea of diversion. It's diversion of water along the front of Okanagan lobe when it advances. So it looks a bit like this. Okanagan lobe advances, and water from glacial Lake Columbia is able to overspill the rim of Grand Coulee and overspill the edge of Lake Columbia and divert along the front of the ice into the head of Moses Coulee, if you can picture that. Okay, again, so Okanagan lobe advances, blocks the Columbia River. That spawns the development of glacial Lake Columbia. Glacial Lake Columbia fills to a point where it spills over the edge. Think of it as the edge of the bathtub, and that water flow is routed along the edge of Okanagan lobe, ultimately connecting to the head of Moses Coulee. That scenario is proposed to be able to convey mega flood scale discharges. But more importantly, there's a critical piece to this scenario, and that is it assumes that Grand Coulee is not breached yet. It assumes that erosion of the Grand Coulee has not been completed yet, and therefore there's a continuous bedrock surface at the head of Grand Coulee during the last glacial cycle. This is a critical, I can't emphasize this enough. This is like a linchpin to this entire understanding of Moses Coulee. It's the fact that it's whether or not Grand Coulee is open during the last glacial cycle or not. And if you talk to preeminent scabland researchers, you will hear both stories. There are some people that view the Grand Coulee as having been open. In other words, it has been eroded and breached to the Columbia Valley, not even during the last glacial cycle, but the one before that. It has been almost forever breached and open to the Columbia River in terms of major ice age floods. But other people argue that no, that breach happened very, very late in the last glacial period. And prior to that breach happening, we have the option of diverting water out of Lake Columbia along the ice front and into Moses Coulee. That's one of the scenarios that exist, and it is entirely dependent, both scenarios, in fact, are dependent on that status of Grand Coulee, breached or not breached. If Grand Coulee is breached, there is no way of getting water over the top of over the edge of the Lake Columbia Basin and into Moses Coulee, because Grand Coulee acts as a siphon. All the hydraulic modeling shows this very clearly. If the Grand Coulee is breached, water is immediately routed through the Grand Coulee, and there's no way of getting water onto Waterville Plateau and into Moses Coulee. So that scenario works only if Grand Coulee is not breached. There's another proposed mechanism, and this one also requires diversion, but in this case, it's during advance of Okanagan lobe, and it requires strategic blockage of, in this case, Columbia Valley, the Columbia River, at the confluence with the Okanagan. So it's the advancing Okanagan lobe that would strategically block the Columbia Valley in order to pond Lake Columbia and allow it to spill over into Foster Creek or Foster Coulee, a major sort of through-going valley system on Waterville Plateau. And if that water can be ponded to a critical elevation of 655 meters, then it spills over into the head of the Grand Coulee. That scenario also requires Grand Coulee to be closed, unbreached. If Grand Coulee is breached, it's game over for diverting water around. It goes right through the Grand Coulee. There's no way of damming it. So both of these scenarios currently require Grand Coulee to be closed. That's an unknown state at this point. Surprisingly, after 100 years of research in the Scablands, it remains an enormous open question as to that status. But it requires that Grand Coulee not be breached in order to divert water.
Lost you. Lost you. Okay.
Mountain lobe could selectively dam this critical portion of the Columbia River and not something else upstream somewhere to allow for this diversion. So these are the two competing existing models, and we're proposing a third one that is really more focused not on diversion, but on the subglacial routing of water. I want to make one more point on this early scenario, and that is the modeling that allows water to overspill and divert along the margin, that predicts a mega flood scale discharge through this diversion. In other words, there's a mega flood volume of water moving across, oblique across Waterville Plateau into Moses Coulee. And what is striking is that when we look at the landscape, there's a total absence of a convincing channel system that allows for that much water to move basically northeast to southwest across Waterville Plateau into Moses Coulee. This would be a channel network that it would be literally orthogonal to all of the orientations of the mapped subglacial channels. We just don't see something that large. Now we can make some allocations, perhaps that happening early on during glaciation, and we bury it partially in sediment as the lobe moves over it. I think that seems like a bit of special pleading. It's perplexing how a channel that conveys so much water, well, doesn't create a channel. That's the point. A route that conveys so much water does not leave some sort of geomorphic imprint. And whether we accept these diversion scenarios, what they don't do for us is they offer no explanation for the mapped channel network that we've illustrated here. We still need to explain this channel network. If we want to invoke just overspill for funneling water into Moses Coulee, what is this other network, this blue one that you're seeing here? What does it represent? And what are its contributions? And none of these overspill scenarios offer any explanation as to how we develop such a well-integrated plateau-wide channel network. That's another big perplexing part. So for our money and for the work that we've been doing and the focus that we really sort of cast on Waterville and Omak Plateau, we're going right back to what Brett's proposed. We're 100 years since his early days in the Channel Scablands, and in the 30s, Brett's wrote that the history of Moses Coulee appears to include an episode of tremendous discharge of glacial water down through a canyon tributary to a Columbia Valley. Brett's was on to these ideas. He already was thinking about water from northern sources down Okanagan Valley. He spent time in Okanagan Valley on the Canadian side looking for evidence of lava flows that might generate subglacial water. We think this is part of that evidence. Brett's was onto this, but what we've mapped for us is solid evidence, we think, of a channelized system, subglacial in this case, that supplies water to Moses Coulee. If we go back a slide or two, I'll just show you. Some of the implications of this mapped network is that some of the water that is produced and delivered subglacially also drains into the Columbia River and also drains potentially into the Grand Coulee. So the effects are not isolated to Moses Coulee. The bulk of these channels do converge on Moses Coulee, but some of them peripherally also converge and contribute potentially water to Grand Coulee and also to some of the features, the scabland features and the depositional features like the big bars that we see along the Columbia River. So it's not just Moses Coulee story, it's broader than that, depending on the magnitude of the flows that are generated and delivered under the ice. And our proposed delivery mechanism and this network of channels is completely independent of the status of Grand Coulee. It works regardless of Grand Coulee being open during the last ice age, or whether it's not open yet and hasn't been breached yet. It does not depend on the status of Grand Coulee, which we can't say for the other two scenarios. And one of the implications is that if Grand Coulee is in fact breached, and it acts as a regional siphon for Glacial Lake Columbia water, it means that there is no Glacial Lake Missoula water or Glacial Lake Columbia water that makes it onto Waterville Plateau. There's just no physical mechanism of doing it. And so we have to look for other places for water. Clearly there's a channel network, and we're proposing that channel network is subglacial with the water produced and routed under the ice sheet. Thank you.
Awesome.